Hello. Yeah, good morning and welcome to this unique live technical discussion series. So for wind engineering, we decided that we will have a three different session. So we already had one interesting session on the low-rise structures, wherein you all have said very positive feedback. So thank you all for the same. Now today's session, we are going to focus exactly on the tall buildings. I think that's going to be very interesting discussion. And the after this session, in maybe in the future session, we will be talking specifically about the wind tunnel testing, and definitely, I think that is going to be even more interesting. So today we have Dr. Abhay Gupta with us, as well as we have Tony from the WindTech consultant. So so before start, I will quickly introduce themselves. So Dr. Abhay Gupta, as you all know, he has done his PhD in the wind tunnel testing for the checking aerodynamic interference effects for the rectangular tall buildings. And he's having almost 35 years of experience for the civil structure design. And he is a director at Skeleton Consultants Private Limited. Okay, and we have a special guest today, Tony. He is working with Wintech, I think since 1991, and he's a
Yeah.
director at Wintech Consultants, right?
Yes.
And interestingly, he has worked on a 2,500 projects. Either he was working or either he was a supervising. So I think he has worked for the projects all around the world, as well as I think including numerous landmark projects. So it is our honor to have you both eminent experts on the board, and I'm sure we are going to very interesting discussion today. Yeah,
Good morning, Tony. Good morning,
yeah,
Bhavin.
Hello.
good
Hi.
morning.
Hi, Dr.
Yeah,
Gupta.
yeah.
Thank you, Bhavin.
Yeah, most welcome. So to start with, can we do this way that Dr. Abhay Gupta can give us very quick overview of IS 875 for tall buildings, and then we have received around 15 to 20 questions from the social media. So those will be taking up in sequence, and thereafter we'll be taking up the questions which will be coming from the live chat.
Okay.
Okay, okay,
Uh,
okay. So over
Good
to you,
morning.
Tony. Yeah.
Yeah. Good morning, all my dear friends who are joining this session and are keen to know more about the wind forces on tall buildings. Every structure which comes in the way of the wind uh, attracts or generates wind pressure and wind force in turn. We have discussed low-rise buildings in the last session. Today we are going to talk about the tall buildings. Though every other structure like lattice towers, chimneys, bridges, or anything else attracts wind. But we are focusing today on tall buildings and our code IS 875 Part 3. This deals primarily with the buildings, though it contains some more structures but very cursorily. Like lattice towers, it gives some idea. Some hoardings also. Hoardings are a part of the building, I believe. They are installed on the top sometimes. And even water tanks kind of structures, we can work with this. But we are focusing on buildings. For the benefit of all our friends, all young engineers, all the experienced people who are there, uh, I started my introduction to wind engineering started in the year 1991 when I decided to do my doctorate from IIT Roorkee under Professor Prem Krishna, Dr. Krishan Kumar, and Professor P.K. Pandey, the great stalwarts of the University of Roorkee. And I learned about the wind, its characteristics, the that time IS 875 1987 was in force, and we were primarily having that document only as our reference. There were no Indian textbooks, basically, Indian reference books. We were referring to those books which I referred in the last lecture also. Signal and Scanner, Wind Forces in Engineering by Peter Sachs. These books were widely referred, J.D. Holmes and others. The Australian book was one of the very good references that time also. Uh, कहीं से आवाज आ रही है डिस्टर्बेंस हाँ so this if you, I'm sure that each one of you have gone to IS 875 party and right from section 8 where it talks about the tall buildings where it talks about the interference first and then the dynamic effects in the tall buildings. So The tall building has a shape in plan rectangular, square, mostly. There are cylindrical shapes also in other shapes too, but mostly they are confined to squares and rectangles. So this code is primarily applicable to the prismatic shape. Tall buildings are rectangular or square shape, primarily, and even cylindrical, even circular cylindrical, prismatic. Tapering buildings, though we can draw some guidelines from here, but strictly speaking, the flow pattern around a tapering building is a bit different as you move up as compared to the prismatic rectangular or square building. The response of the building in the direction of the wind has been termed as along wind response, and the response perpendicular to the flow direction is termed as across wind response. Along wind response sometimes is also termed as drag. It is dragging, the wind is dragging the structure, so drag. And in the crosswind direction, it tries to lift up. So that is also termed as lift sometimes. But drag and lift is more commonly used in the aerodynamic field rather than the buildings. In building, we use along wind and across wind response. There's a third response also, torsional. When the building face are wider, then the force at all points in the windward face, you all understand, the face of the building which is facing toward the wind direction, onset wind direction. So if the width is large, then at all points we do not get the wind pressure uniform value. There is a difference, somewhere maximum, somewhere minimum, and because of this, a torsion is also generated. Now this torsion is difficult to mathematically document so far. So it is not a part of the code except a small statement that torsion should be examined through wind tunnel testing for such and such type of buildings. Similarly, in the 875 1987 version, only along wind response was the main focus, and a crosswind response was introduced later on when more knowledge was obtained. Even today, the knowledge about the crosswind response, theoretical knowledge about the crosswind response, which is documented all along the world, is specific to that kind of a structure. We'll discuss more on that as we move ahead. However, when we start with the code, the first thing is given as hourly mean wind speed. So there are queries about that. And the basic wind speed map figure 1 is 3-second gust wind speed. There's a difference. And for the tall buildings, owing to their frequency range, owing to their natural period range, we are considering hourly mean wind speed for their response. The next section in the code is about the definition. What should be a tall building? So a height to depth ratio has been given and a natural frequency less than 1 hertz has been identified to be qualifying as tall building. Third is calculating the time period. It is very clearly mentioned that time period should be analytically obtained through detailed analysis or the field measurements, but if nothing much is available, then you can use this formula. So there are two types of the expressions given. One is for the framed buildings and another one is for the all other buildings. All other means infill walls or shear wall buildings and all those. Means where there are more stiff elements. So there are two expressions given. The first expression for bare frame is different than what is given in IS 1893. Why is it different? We'll talk more on that as the queries come. Then comes the along wind response. For along wind response, Indian code is adopted Gust Factor approach developed by Alan Garnett Davenport, one of the pioneers in the field of wind engineering, though he is no more, but we had the opportunity of meeting him in 1995 9th International Conference on Wind Engineering in Delhi. He came there and we had an interaction also. So the method developed by Davenport in 1962 to 1967, that is called as Gust Factor approach, is still valid and is being used. Though some more approaches have been subsequently developed by Solari, Simeon and Scanlon, but primarily Gust Factor approach is widely accepted. Why is it called Gust Factor approach? Because in the tall buildings, the response is comprising of two parts. One is a static part and one is a dynamic part. The dynamic part is primarily calculated using the Gust Factor. What is that? We'll discuss more. So moving ahead from the Gust Factor approach, then now recently the crosswind response has been introduced. If you study the code, then for a crosswind response also, the some curves are given. Those curves are experimental results. As such, there is no theoretical formulation. Some attempts have been made using the statistical analysis and some database kind of the approaches. So they are also being crosswind analysis is there. Acceleration has been given emphasis in the code. Acceleration at different levels at the in the along wind and across wind direction, because ultimately it is the acceleration which affects the occupancy. The displacement affects the design and acceleration affects the occupancy. These two things. A new chapter has been added recently in the last version of the code, which is interference effect. So interference is a very, very vague phenomena, but it is definitely a phenomena. Our expert today, Dr. Tony Roffel, will explain you more on that. That while performing the wind tunnel test on several buildings across the world, we have observed the interference to play a major and critical role in the design of not only the new building, new proposed building, but also on the design of the existing structures. The existing structures also get affected, and there have been legal cases because of this in past. So this is basically the tall building part of the IS 875. And Bhavin, we can take up the queries now.
Yeah, yeah, yeah. Thanks a lot for giving a very quick introduction. Now we have received very interesting questions when we floated this event in the social media. So that will be taking it up sequentially one by one. See, first question, which is a very basic question we have received, that when the building should be considered as a tall building. Yeah, yeah,
Tony, please.
yeah.
Yeah, Dr. Tony.
Maybe I can add. Okay, so in IS 1670, okay, in section, let's see if I can share my
People are aware of that. You can even straight away convey that.
Okay, no need. Okay, all right. So in section 6.2 of IS 1670, it says it here that it's defined as any building above 50 meters, which is consistent with what Dr. Gupta mentioned, anything with a frequency less than 1 hertz, and that is essentially the same thing. There is a very simple rule of thumb that relates height of building to natural frequency, and this is 46 over h in meters. So when you have a h close to 46 meters, you will get very close to 1 hertz. So they're one and the same thing.
I request you to explain this 46 over h a little bit more, because in India we are not aware of this particular data.
Yeah, this is based on a very extensive database of full-scale measurements of actual buildings measured in the field, and was done from the late 80s to early 1990s, by the University of Sydney as Professor Kwok at the time. And he found that this is quite a very reliable indicator. What we tend to find is also from our measurements in the field that this matches quite well. FEA modeling, if it's done very well, comes very close to 46 on H. But what we tend to find is if it's done in a simplistic way, not accounting for any contribution from perimeter columns, for example, we tend to see the estimation from FEA models come a bit lower in the natural frequency than the 46 on H rule, typically by up to about 20% lower.
This 46 over H is, I believe, true for the framed buildings.
Yes, it's for, yes, we're basically for tall buildings where the core is the main lateral force restraining element in the building.
But not for the shear wall buildings. Shear wall buildings will have more stiff value.
Yes, but not a big departure from 46 on H still. So maybe a bit, yeah. So I think as a guide, somewhere between 46 on H and 80% of this is anything in that range is a reliable estimate. But from experience, 46 on H is usually pretty accurate.
So
It's
for
a simple
tall
rule,
building
but it actually seems to be quite accurate.
So for tall building definitions, we can summarize that buildings more than 50 meters, buildings having height to lateral dimension 5, more than 5, and buildings with natural frequency less than 1 hertz. These three things, if qualify any one of them, the code doesn't say all of them. They say any one of them will be considered as tall building. Now, I means everybody who is a user, a designer may have a question. If suppose a building is 50 by 15 plan and 50-meter high, then should it be called as a tall building? Then it will, as per IS 875, it doesn't qualify. But as per IS 16700, it qualifies. So probably those points in future can be taken up. But as of now, a building with 10 by 10 by 50-meter height would certainly qualify to be a tall building.
Right.
And any building more than 50 meter, there can be an engineering judgment also, that depending on the plan dimensions.
Right.
Okay, we move on.
Right. Okay. So another interesting question which we have received, that when we talk about, I think we have already touched upon this area, but the question was that when we talk about empirical time period formula, then it is different in a earthquake resistant design codes and it is different in the wind codes. So so which formula should we refer when we are calculating the wind force? That was the question.
If I explain it a bit more, if you refer to the first formula 762A of 1893, it is 0.075 h raised to power 0.75.
Right.
If you convert that, it will come something like 46 over h.
Okay.
It will come to in that range. In that. Now, if you take the wind code 0.1 n is number of stories. If I say each story is say 3.5 meters, right? Then a 15-story building would be about 50-meter high.
Right.
So my 50-meter building, 15 floor would be 15 into 0.1 is 1.5 seconds, which is less than 1 hertz. Okay. If I see 46 over h there, it will be 1 second. 46 by 50, it will be 1 second. So basically, they are close by.
Right.
0.75 h raised to power 0.075 h raised to power 0.75 or 0.1 n or 46 by h are more or less in the similar range. But as Dr. Tony very rightly said, if we can do an exact analysis through FEA, and nowadays the tools are available, so we can even get a good judgment on that. But the best thing is, time period is something which is dependent not only on the frame, but on the infill, on the mass. So a field measurement certainly is more authentic. And I have a paper from Sydney, I think, or Japan, where about 100 buildings were monitored, and that natural period has been plotted, height versus that, and that comes around this only. For framed building, 46 over h, and for shear walled buildings, it was something like 70 over h or something like that. So, as such, there is no difference in the formula, except that 762B. In earthquake, those things play much role. So, they have divided into 3. Wind people are more generous.
Okay, one more interesting question which was mentioned, that for calculating CF, A by B value in the graph is given maximum 3. So now what will happen, or what should be considered for the higher A by B value? So whether the same graph 4A with the restricted value is taken?
Can you show that graph?
Yeah.
Figure 4.
I'll just open it.
Yeah, figure 4. Basically, that's a limitation. And other codes, I think Australian code, Tony, you have formulas.
The Australian code doesn't go past the 1 to 3 aspect as well. And in fact, the new code that's about to come out in Australia will be excluding buildings with a longer plan aspect ratio from being covered by the code. So there's a limit, and I think especially that the Indian code doesn't cover torsion. I would be very careful not to, if you have a building with a longer than 1 to 3 aspect ratio and substantially higher than 50 meters, then you should be very careful, because the torsion loads can be very substantial here. So just use with care if you have longer than 1 to 3 aspect ratio in general. So and seek specialist advice, because the load from torsion can be very substantial here.
Yeah. Now looking at this, it says A by B, the plan aspect ratio up to 3. So primarily, it means that for plan aspect ratio more than 3, straight away these values of CF may not be.
As a first pass, you can use 3 still if you have 4.
The first pass, you can use because beyond 3, beyond 3, if you see, they are going to become parallel to horizontal.
Yes, I agree.
So more or less the same CF value has to be used. But there is a debate going on with the plan aspect ratio 0.6, 0.7. There is a peak. Look at the peak. And the CF values are very, very high. Referring to some other international documents, these values are not as high. So probably next revision of the code, this will be replaced by a formula. But as of now, yes, what the question has been asked, for higher A by B values, whether same graph 4A with restricted value is to be taken. Yes.
Right.
Yeah. Just be careful with torsion though.
In torsion.
And as a rule of thumb, you may want to refer to the ASCE or the Australian AS 1170.2 for guidance on torsion. Which says in both of these standards, the torsion is a function of the along-wind response. And it's generated by offsetting the along-wind point forces by anywhere between 0.15 to 0.2 of the width of the building. And you'd offset, obviously, in either direction to see the effect of that.
Correct. Similar to accidental eccentricity in earthquake.
Yeah, so, and this is in the Australian code that was derived by WindTech based on a large number of actual wind tunnel tests of real buildings. Keep also in mind that there are the odd cases where you can get a bit higher than these numbers if it's a very long aspect ratio in plan. So just be careful with those long aspect ratios.
Correct. Right. This next question is very interesting, and I'm sure Dr. Tony Rockwell has a lot of information on this. Aerodynamic modifications.
Yes, there are very good tricks that could be implemented and have been in the past on some of the very tallest buildings in the world. And a lot of it obviously has to do with the shaping. So the shaping of the tower has a very big impact, more than the structural system. Okay, so and that is usually when you're dealing with a very tall building, it's very good to have this interaction with the architect to try to come up with a scheme that isn't going to be very penalizing from a cost standpoint. For example, one simple thing that is implemented, you'll notice for the very tall buildings, there's little steps in plan as you go up. So at the top you see it's narrow, then steps up as you go down, and you see that also in some of these very old Indian architectural remnants, such as the wind palace.
Type 101 is similar.
Yes. So basically by providing a 10% step in the top quarter of the tower, or top third of the tower, you could potentially generate a almost 50% reduction in your crosswind. Now, the crosswind for a tall building is often the more critical than the long wind. So this is a significant cost advantage. And by not doing it, it could leave the project to be unviable. So it's very important to look at the aerodynamic forms. Stepping is not the only solution. Corner treatment, like putting steps at the corners themselves rather than complete steps in plan, is effective. Roughly half as effective as complete steps, but still quite effective. Or changing the shape, so basically changing from a square to a octagonal shape or circular shape, or even changing from square, circular back to square. But the idea of changing these shapes is because the vortex or the wake shed around the building, which is what causes the large crosswind forces, is a function of the shape, but it's also a function of the width. So if you change either of them or both, what will happen is the vortex is not going to be it's not going to be at the same frequency all the way up.
Yeah.
And what will happen then when a vortex bubble forms, it will not engulf a large part of the side face of the building. So imagine you have a large pressure bubble multiplied by a huge area. You get a area times pressure, you get very large sideward force. Okay, that's what you want to avoid. Absolutely. Okay, so by changing the width gradually as you go up and or shape, this bubble becomes very, very limited in its area for any given time instant, and that is what can cause a very significant reduction in your crosswind forces.
So whenever there is an opportunity, because in India the practice is a bit different. Here, first the architect finalizes everything and then gives to the structural consultant that whatever fantasy I have thought of, you just do the structural engineering. The structural inputs at the form finalization stage are very, very important. So if
It's important. It's good to engage with the wind consultant at the concept design. It makes a huge difference to the project bottom line.
So if that opportunity comes there, or if not, you should generate that opportunity to. Nowadays, even without going to the wind tunnel, there are some very good software available which gives you a preliminary analysis of the CF value for different shapes. You can refer to some published paper also, but there are. I was attending a webinar recently. I'll recall that building in Mumbai, near Mumbai, where the architects did an excellent exercise along with the structural engineer to finalize the shape of the building. I'll convey to Bhavin later on. I have got that presentation, I think.
Yeah.
So that is one thing. This question has two parts. One is, can you throw some lights on the calculation of gust forces? We have answered the second part. This light on the calculation of gust forces I am parking as of now, because there may be more queries on this. So that time we'll take up this.
Definitely. So the next question is in the similar line, like what it says that if possible, please discuss regarding the gust factor, whether it should be similar, same value for the entire height, or it will vary based on the height.
What do you say, Dr.?
Yeah. Okay. So if you follow the exact letter of the Indian code, every segment, because for the Algonquin, you need to break up the tower in sections, right? Each section needs its own gust factor to be calculated for that area. Okay, so yes, it varies, but you will find that over the height, the variation in the capital G gust factor won't be very different over the height, but there will be some variation as you go up, and it'll be slightly increasing as you go above the ground.
Yeah. Formulation is like that.
Yeah.
For crosswind, of course, it's different because you need to calculate the response of the entire structure. Okay, and then it gets scaled as a whole. So, but for the along wind, it's segment by segment.
And why is it segment by segment? That also I would like to say. Basically, this gust factor, the gust value depends on the turbulence intensity. The fluctuations in the onset wind, and they vary along the height.
Yeah.
Correct. The entire building has one dynamic property. Its natural period is 1. Its damping is 1. That is 1. But there are two contributors to the dynamic response, to the gust. One is the gustiness of the wind, and one is the dynamic nature of the building itself. Now, the dynamic nature of building is uniform throughout, unless and until there is a change. It is a stepped building or so. But otherwise, in stepped building, certainly the change, there is a variation in the gust factor along the height. But since the turbulence intensity varies along the height, so there is a change in the gust factor value. But as Dr. Ronnie says, if it is only because of the gustiness in the wind, the change is not much from bottom to top. You can go ahead.
Right. The next question was like, what could be the impact of, let's say, interference effect on design of the tall buildings?
Yeah.
Okay.
Please, Tony,
Yeah,
give
sure.
some examples where you have
Okay.
significantly observed.
Yeah, sorry. This is one of my pet subjects. So, yeah, so the interference tends to be more pronounced in the more open terrain. So if you are in the middle of Mumbai, okay, and you have tall buildings in in high density, interference effect is not very likely. If you're near the coast of Mumbai, however, rather than the center, and you are open to the prevailing winds coming from the ocean or the sea, and there is nothing much between you and another building downstream, okay, this is where you get the biggest impact in terms of interference excitation. And the lower the upstream turbulence, the higher this effect is. And as a rule of thumb, the critical distance is somewhere between, first of all, the widths of the two buildings need to be similar for this to have maximum effect. And the shape obviously similar, both rectangular. And also the distance roughly between 4 to 6 or 7 building widths distance apart. And the reason for that is that's where the vortex from the upstream building has the biggest impact on the downstream building. So that's really the main criteria. And the effect to expect is you would expect to see potentially up to 50% increase in the dynamic part of the response. So if we're talking about crosswind, that could be a full 50% increase. In the case of a long wind, it'll be less because obviously there's a static part of the response in the peak, but the dynamic part of that will be increased by up to about 50%. So the 0.35 factor in the code is fine, except if your building is governed by crosswind, then you need to be careful because that could easily come up to 50%, be 1.5 in that situation. So that's essentially a very brief summary.
Yeah, it's a very exhaustive subject, and as such, no theoretical formulation is there. But certainly, there is an adequate number of experiments done on the models as well as on the even the full-scale measurements also have shown that there is a significant impact of interference on along wind as well as on the across wind. There are certain situations where shielding is also there. Interference is not always due to the building which is upstream. If a building is constructed downstream, then too there is an interference effect on the upstream building which is already existing. It's a very, very typical thing because of the nature of the wake flow which is there in between the two. So
Yeah,
more
it's normally, there's been very rare cases where the upstream building is also affected. But this is only, and this is due to a mechanism called the lock-in excitation mechanism. And it's only where the upstream building is a very close proximity to the downstream building.
yeah, I
And,
have
and, and
observed that
offset, yes.
in
And,
case of short upper body orientation, suppose my
yeah,
building is
but,
3 to 1
but in the vast majority of cases, the impacted building is the downstream building. Now, obviously, depending on the wind direction, either building could be a downstream building, okay?
yeah,
But the important thing to remember is the upstream turbulence. If it's a low turbulence, the building that's on the side of the sea, for example, is going to cause more impact than the building that's on the side of the built-up city area.
okay.
Yeah. So the next question is also, I think, in the similar line, that in practice, at what situation interference effects are considered in calculating the design wind pressure or forces, say along Fx and Fz using a Gust Factor method?
Okay, so the effect of the interference on pressure is still there, but to a lesser extent. And that's because the pressure is influenced a lot by local turbulence. So the wakes shed by the actual study building itself often have a bigger impact than the wakes of other buildings. There are, but not as significant as impact on the overall response on the structure.
Right. Okay, there was one interesting question that if we talk about Indian Standard Code, then whatever specific values which are given for the wind forces, are they higher than the Australian, New Zealand code or say American code or say wind tunnel analysis? And which do you think is more reliable?
Okay. Look, the provisions in the Indian code are very much modeled on the ASNZS, Australian New Zealand standard. Okay, pretty much mimics the Australian standard. There are some tweaks in the current version, which provide some small adjustments. So I guess in a way they are a little bit more elaborate, but generally very similar. In terms of accuracy, nothing is more accurate, of course, than a wind tunnel analysis.
Yes.
However, I want to highlight something that a long wind response is actually generally quite accurate in the codes. However, if the building shape changes significantly from a rectangular form, using the standard for these buildings is quite risky. And in fact, in IS 1670, it does actually prohibit the use of IS 875 in these other buildings of other forms. In fact, it goes beyond that, saying not recommended for buildings above 150 meters. You may find that in section 6.2.
Right. 16700 really mentions that.
So I'll just read it out. With height greater than 150 meters, okay, or with complexity in plan or elevation geometry, or sited in complex topography with group effect or interference effect, existing or future potential, or with a natural period greater than 5 seconds. Now, nearly all of these are exactly the same in other standards, like the Australian standard says very similar exclusions for the code. And that's the reason for that is once you go much higher than 150 meters, very small changes in the building geometry can have a very big effect on the crosswind response. And these are very difficult to standardize, very hard to get an accurate standard prediction. In fact, You may recall I just said the along wind is quite a robust prediction, but I can't say the same for the crosswind because it's very sensitive to any small departures from a rectangular prism. For that reason, it's not recommended to base a design on IS 875 if you find that the crosswind is governing the design. And I would strongly encourage you to see this as an indicator that this is a trigger to look at more accurate means of modeling the effects on this particular structure, which is using the wind tunnel testing. So your most you may see this is a background to put a plug for wind tech consultants, but that is the reality. Okay, there is so much that the codes can cover. The codes cover simple rectangular forms to a reasonable extent, but not every building is a very simple rectangular form, and small changes can make a big difference.
I believe this question is also being asked for the low-rise structures pressure coefficient values.
Yes.
See, the pressure coefficients which are documented in the code are drawn from the actual wind tunnel tests on the simulated models in the simulated environment, scaled models in the simulated environment. And all these have not been done in India. Whatever values are there, they have been picked from international literature. And most of them are, as Dr. Tony said very clearly, they are matching with the Australian code. We have the similar values. So the experiments done anywhere in the world are authentic and we can pick up those. So that was the thing. The only care user has to take, since we are using while calculating, we are multiplying these coefficients with the design wind pressure, which is obtained based on the gust wind, 3-second gust wind. So any other code to which you are comparing should also have the same 3-second gust wind pressure. You can refer, the user can refer to a document which was, an exercise was done in 2006 in India, harmonization of the international codes on wind engineering. That workshop was done in 2006 in India, and those proceedings must be available somewhere on the internet. Harmonization workshop. So there, 3 problems were identified: one low-rise, one mid-rise, one high-rise, and these 3 building problems were solved using some 8 different country codes, and the results were compared. So basically, all are similar depending on the averaging period which has been used. As far as reliability is concerned, the reliability is reliability of the wind tunnel test which has been conducted, nothing else. So during the code, there is no question of having a reliability factor there. Only with the actual field test you can verify that if the code gives this value, how much is actual field value, and that may always vary. That may always vary.
Yeah. Okay. So there were a few questions from Akash, and in fact, he shared one PDF file. So I'm sharing that PDF file, and if possible,
Let me know what Akash does.
Yeah.
Is a student?
So I'm not sure whether he is in this stream or not. Yeah.
Okay.
Yeah.
No, whether he's a design engineer, experienced engineer, or is a student.
Yeah, I think he's a junior engineer. Might have around 3 to 4 years of experience, I believe.
Okay.
Okay. So just let me share the document. Yeah. Just a minute.
Yeah.
Yeah. So these were few questions. I think we can directly go to the second question. What could be the right way to apply component on tall building?
No, even the first question also we can address because he has taken a reference from
Okay.
a celebrated book,
Okay.
difference between static wind load and dynamic wind load. He is writing that from Taranath book, it
Hmm.
says time taken by wind maximum intensity diminishes to zero if this time period greater than building natural time period is called static wind, and
Hmm.
if less than it is called gustiness of the wind.
Hmm.
See, the time period of oscillation of the building is important. Correct. If my building is flexible, if my building is dynamically vulnerable, and the dynamic vulnerability or susceptibility is because of those two parameters, height more than 5 and frequency less than 1 hertz. If the building is is about to oscillate in a lateral force, then a dynamic response has to be considered. If the building is rigid, stiff, much stiff, then only the force divided by the stiffness of the structure is the displacement, which is directly a static response. In that case, even the onset wind, which is fluctuating, wind is always fluctuating. The structure may be rigid, may be flexible. So if the structure is too rigid, then my pressure fluctuation may be there on the building face. And accordingly, my base bending moment and shear forces and other things can be fluctuating. Correct? But the dynamic response will not generate in the building. The displacement and acceleration will not be there. So, depending on the characteristics of the building, the response would be either static or static plus dynamic, both.
Right. Okay. So the second question is related to application of wind force in the software, and he has shared snap of the software here. But I think again he's talking about application of wind force on a diaphragm.
Actually, in ETABS,
Mm.
you can apply, when you say the automatic generated wind, it applies on a single point on diaphragm. But as a user, see, a software is always something like garbage in, garbage out.
Right.
If that is giving a flexibility to give you apply all the force at one point, the results will be according to that. But you have the choice to apply that wind force at several points simultaneously. And since, as I explained in my last session also, since the wind is generated because of the exposed area of the building coming in the way of the wind force should be applied as a distributed load, not
Right.
on a single point. And I suggested also that Akash can do an exercise by
Mm.
applying the entire wind force like this as in the E-types auto generation,
Mm.
or by splitting that wind force at several nodes in the on the windward face on
Mm.
that. And then you
Okay.
can see the difference in the result. He himself will be able to appreciate the
Mm.
correctness of the application.
Right. Right. Okay.
And he is also writing it is the wrong way to apply. See, logically, wind is
Mm.
not applicable at the center of the diaphragm.
Mm.
It is not.
Mm.
Unless it's a very tall building. If it's a very tall building,
Yeah.
and then you simulate the loads to a point, say
Correct.
at the point the center of rigidity, as long as
Yeah.
obviously
It's all
including a
something.
torsion component as well, then what Dr. Gupta said is true for low rise, mid rise, for very tall buildings. What happens is, because we're applying these loads all the way up to the top with a component of torsion, they would tend to have the same effect. The effect will not be very different. I mean, and as Dr. Gupta did suggest, I think it's a good exercise to see what happens if, for example, you split this point load that's at the center to 4 equal loads at the corners, for example. You'll probably will see a difference, more of a difference if it's low to mid rise, but probably not much of a difference for a high rise building.
A building which is flexural building, basically, a tall building which
Yeah.
is primarily behaving as a cantilever, vertical cantilever, which will be more than 150-meter tall, I believe. There, the difference may not be significant.
Yeah.
But below that, yes, there would be a difference.
Right. Okay. His
Please
third.
discuss all parameters in Gust factor and basic thumb rule to check this factor.
Yeah.
Okay. Uh, I would just give a background and then I'll request Tony to explain more.
Yeah. Okay. So this is the Gust factor,
Gust
and so this Gust factor method is applicable to the along wind response. Okay, and the along wind response is affected by two very important mechanisms. So obviously, or three actually. There's the mean, which is the static part of the response, plus, and this mean here is the number one. So this, because you're multiplying the mean by this whole factor, then you're saying one means the mean plus the following. Okay, so the following, the part, this next term here is the dynamic part. Okay, so the dynamic part consists of two key parts. Okay, there's the background response, which is the first term that you see here, which is why we call it the B for background. And the next part is the resonant response. Okay, so resonant response is, okay, so what is the difference between the background and the resonant? The background response is the same effect that any building sees, whether it's low rise, medium, or high rise. It's the dynamic action of the wind on the building envelope. Okay, so that's the dynamic action from the wind on the surface. Okay, so this is the background response. The resonant part is what happens to the overall peak response due to the flexibility of the structure itself and its response. So it's very similar to if I simulate this to someone pushing a child on a swing. Okay, if I push someone, suppose this is the swing going from left to right. If I push someone at the same rate as the swing goes and comes back, okay, then that person will swing higher and higher. So the swing, the natural frequency of sway of the swing can be simulated to the natural frequency of the tower. Okay, and the person pushing the swing is the dynamic action from the wind. Okay, so the dynamic action of the wind pushes at a certain frequency, which is a function of the properties of the wind. It doesn't change, right? But what happens as the natural frequency of the building becomes smaller and smaller, its actual frequency becomes very close to the rate at which the wind is pushing. Because the wind pushes somewhere between 0.1 of a hertz to 0.05 of a hertz. It's that's the cycle rate in the natural wind. Okay, unless it's an interference excitation where it can be a lot higher. Okay, so that if the swing is coming and I'm pushing here, and then at some point it's coming back here, and it's at halfway, I'm pushing there, and it's very random. Okay, then the swing isn't going to go very high. But if we're pushing at a fairly similar frequency, that's the effect of that's where you see the resonant part becoming very high. Okay, so we go back to the formula. Well, you'll see this term here becomes more significant than the background as the building height increases. Okay. Now, why are they in a square root sign? It's because the background and the resonant parts are actually, these are the square of the standard deviation response. Okay, so we're adding them as a vector sum. So to add the background and the resonant must be added as a vector sum. So you take the sum of the squares and take square root, and that becomes the total of the background and the resonant.
Bhavin, is it possible that I can show something from my system?
Yeah, definitely. Sure. Definitely. You please, you will have an icon of a share screen at bottom. You please click on it, and then you'll be able to share it.
Okay. Whatever Tony has said, I have a
Hmm.
small diagram to show that. It comes
Yeah,
from the Davenport's method itself.
yeah, yeah,
Screen sharing works best. This. Okay. Share screen. This and this one.
yeah.
So
It is visible to us now.
it is visible to you. This is the basic development of the Gust factor approach. If you look at the top three, there is a velocity fluctuation, then the force fluctuation, which is in concurrence with the velocity. If you see the pattern, but the magnitude is amplified because it is v square, and then the response, which is again another fluctuation. There is a gust spectrum in the second row. Gust spectrum has some frequency distribution. Then there is an aerodynamic admittance. Aerodynamic admittance is basically the gustiness of the wind. That is the force component, the energy component. Third one, aerodynamic force spectrum. Okay. When this aerodynamic force spectrum works on the structure, then mechanical admittance is nothing but the structure's dynamic property, enhancement. Those who are familiar with the machine foundation design, they know this term mechanical admittance very well. And then some spectrum are matching with the structural frequency and some are not matching. So the overall response is composed of two parts. If you look at the last diagram on the right side in the second line, it takes an initial part, comes down and then there is a peak. So if you consider these to be as split into two parts, that one is a peak and then goes down to zero, and then there is a small hump at a particular value. That hump, the peak at a particular value, is corresponding to the structural frequency. So the overall response of the structure composed of three parts. One part is static, which is not part of this diagram, which is one in that formula. Then there are two parts. One part is a background response, as Dr. Ni explained, which is corresponding to the response generated in the structure because of the non-resonant frequencies of the aerodynamic spectrum. And the third one is the resonant response, which is generated because of the resonant frequencies of the aerodynamic force spectrum. So this is the development of the Gust factor, and hence when the formula which is there, the expression.
Yeah, so the area underneath those last curves, by the way, that Dr. Gupta showed, are actually equal to the variance of the response.
Yeah.
Okay, so which is what? So it's the sigma squared.
So one is the static part, one plus the second and third term. Second is background response, and third is resonant response.
Yeah, so the background was the simple hump that you saw, the one with a very sharp point, that's the resonant. Okay, that's the property of the building itself, and then the two are combined in the final response in that same curve.
Now
But because the area,
there are certain parameters in this formulation. I'll suggest Akash to rather than asking us to discuss all parameters in Gust factor and basic thumb rule, I'll suggest Akash to use this formula on some building problem. If he doesn't understand any specific term, then we can reply. Like GV, GB, they are the peak factors. Here it is not 1 plus G, it is 1 plus 5 inside
there's a typo. Yeah.
There's a typo error. In amendment 1, it was clarified. And then other terms are there. Beta damping, as is size reduction factor, E is the energy component, which is depending on the length scale of turbulence. L, there is one parameter in the Gust factor approach, length scale of turbulence. Now, when Davenport developed this method, originally in IS 875 1987, Part 3, we adopted as it is the Davenport's Gust Factor approach for slender line-like structures. That was the original development. So it was considered as if the structures are too tall, very slender. Very slender means there are two things behind that. Very slender means there is no loss of correlation across the face of the structure. Means it is so slender that the entire face is subjected to a uniform gust. Second, the size is such that the atmospheric turbulence eddy, the size of eddy is so big that it is enveloping the entire structural dimension. These two assumptions are there, and if you see in original code 87, L value was given as 1200 meters, 1200 meters, which was too huge. And later on, when even I investigated, I found that a different size of eddy, if actually there, makes significant difference on the response. And that is where the code computed along wind response and the wind tunnel tested along wind response, they differ because of some of these things. When we actually model the energy spectra of the onset wind in the wind tunnel, we also measure the length scale of turbulence and then try to see the difference. So now this method has been refined for the loss of correlation and some more things here. So I'll ask Akash to send us the specific queries, specific difficulties, if any, while using this formula. What is he writing? From my experience, many of people just blindly follow every parameter in Gust Factor. There is no harm in blindly following. Unless and until you are deep into the phenomena, you have to consider the things written in the code, but with some basic knowledge, some explanation. Otherwise, going deep into that, you have to be a wind engineer particularly and study more.
Yeah. So the next question is on turbulence intensity.
Yeah. Now here if you see, if carefully seen, the formula for terrain category 1 and 4 have been written first. And they are also not written. Basically the turbulence intensity has been measured, drawn, curve has been drawn, and a graph has been obtained, logarithmic plot. Depending on the z at which height the turbulence intensity is measured and z0 which is the roughness height. So for 1 and 4 it has been derived, and then 2 and 3 it has been interpolated. As such, whatever values in IS 875 part 3 turbulence intensity values are not given, but in some other codes they have been given also, corresponding to each terrain category. But now with these expressions you can work out. They will come some in the range of some percentage. Maximum may go up to even 40% in terrain category 4. Am I correct, Tony? Turbulence intensity.
Yes, that's right. Yeah, near the ground at terrain category 4, it'll high 30s, or mid to high 30%. Yeah.
So these are basically actually measured data then converted to the expressions.
Right.
Naturally, turbulence would obviously drop as you go higher, and with less urban development. So open terrain is very low at the high elevation, and then increases as you come to the ground because more turbulence near the Earth's surface.
It suddenly reduces. Just above some level, it suddenly reduces.
Right. Yeah. So the next question is again, I think it's in the same line, that why this Z.1, Z.04, this parameters.
Z0. Why Z0 parameter are according to terrain category?
Yes.
Tony, would you like to?
Yeah, I think you explained it already in the last one. It's the okay. So that's the roughness length. Z0 is the roughness, is the effective roughness length. Okay, so so the effective roughness, because we are dealing, the Earth's surface is like a boundary layer. Okay, so and as the wind moves over the Earth's surfaces, there are different roughnesses. You have movement over the sea. That changes the turbulence profile very much than, say, movement over a urbanly dense area. Okay, so the effective roughness length is very small when it's over the water. Okay, and these are based on numerous full-scale measurements. And what you're seeing here in these formulas is essentially a regression fits, if you like, to full-scale observations. So there's nothing more than trying to replicate what is happening in the real world. So we see more turbulence near the surface of the ground, and then it drops as you go up in a roughly logarithmic pattern. And then as the turbulence, as you go to sort of more built up surrounds, the turbulence starts higher and drops off as well. So, but as you go up higher, again, regardless of what terrain you're in, the turbulence will drop. So this is essentially an expression of what is being observed in the real world.
Okay. Why design pressure PD shall not be less than 70%? Akash, basically, some of these kind of riders are a discussion outcome of the code committees. Basically, in a code formation committee, there are several people from several streams and several parts of the country, and each one has an opinion. Somebody must have raised the point that if you apply so many of the factors, then sometimes the actual design pressure may even come less than 50%, which may become dangerous for the structure in some situations. So they might have agreed that okay, it should not be less than a particular value. Now, why is it 70%? Why not 75? Why not 65? No debate, because such percentages they don't have any serious logic.
It comes from the wind tunnel test again.
Yeah, unless and until there are some evidences.
You don't want to be less than the wind tunnel results, basically.
Yeah, well, that is given in 16700.
Yeah.
That it should not be less than wind tunnel test and all those things are there. But 70% is okay. I believe 70% even is less. It should not be less than 80% or something.
In the Australian code, it says not less than 80%.
No, so
the combination. We have the same have the same factors in the Australian code. We have the KD, KA, KC. Okay, KA area reduction factor. KC is the combination reduction factor. Okay, KD is the direction multiplier.
So he is asking importance of
in the Australian code, the combination of KA and KC should not be less than 0.8 or 80%.
Would you like to explain these three parameters, KD, KA, and KC?
Okay, so KA is the area reduction factor. Okay, so the larger the area, the larger the effective area, the smaller, because the peak pressure is not very well correlated over the entire area, then you can apply a KA. So if you are looking at a structural member that supports a very large section of a roof of a warehouse, okay, then that the tributary area, suppose that has a tributary area of 50 square meters. This large member will not be affected by a small vortex at the leading edge of the roof. Okay, it's going to be affected by a larger scale vortex that goes over a big section of that tributary area. Now, the reality is the size of that, because of the size of that vortex, it doesn't tend to result in as high a peak pressure as the smaller scale vortices that occurred at the leading edge, for example. So because of that, there was a correction. So because we recognize that the vortices that come over the roof, and they look like a wave, like a rolling vortex. This wave runs from one side, from the leading edge towards the downstream direction. Okay. So because the instantaneous peak averaged over this tributary area, is never going to be as big as the instantaneous peak experienced by one sheet of cladding, for example, at any point on this tributary area, then it was established that we need to put a reduction factor for these large members, so we don't over-design them. Okay, so this is what the background to the KA. The KC is a combination factor. So for the same reason, we are looking at a tall building, for example. You have wind hitting the windward face, creating a suction pressure from behind, both moving the structure in the same direction. But the peak action of the wind on the windward face doesn't always occur at the same instant as the peak suction behind the building. And because of that, when we're combining the windward and the leeward, we can apply a KC factor, okay, because there are more than one effective area contributing to the same load effect, and to account for some lack of correlation of these peaks, then we can accept this reduction. Does that answer my question? Okay.
Yeah, as explained in the code itself. If you look at the KC explanation, it is given there that external and internal pressure may not simultaneously reach a peak at the same time. So the action combination factor 0.9 has been recommended. That's perfectly.
Yeah, and which is very consistent with what's found in the wind tunnels.
Yeah.
Okay, next question is, there is always confusion to yield exit value through this graph. Is it possible to convert in some kind of table?
It is coming. The formula is coming next revision. But as of now, if you do a slight error here or there, there is no harm. See, you can always take an approximate value of CF. If you are using a CF 2 or 2.02, it doesn't make a difference. It depends on the type of the structure. You may be a little conservative sometimes. That's perfect. So it is not the wind only which is there. It is an overall combination of several other loads. So whatever value you get from here, it is acceptable.
Right.
Akash works with PEB pennar or what?
Yeah, I'm not sure.
Somebody else's code he has taken.
Okay, I think this is the last question from inside. Why along wind force component is less than the across wind force? So another point what is making that many MNC company following across wind component forces from ASCE 7 load combination. Why Indian code is not sure about this?
Oh, okay. That's a worrying question, because the ASCE doesn't have a crosswind provision. It does have a load combination for a long wind and cross, but it doesn't. I'm hoping whoever asked this question is not using these load combinations as meaning the crosswind. No, I hope not. Anyhow, but the crosswind, it is very well known that for the taller buildings, and because of the example I just explained with the swing, the vortex bubble that's formed on the side creates a big suction on one side of the building. And then that area of this bubble multiplied by the value of the suction pressure creates a very large force perpendicular to the direction of the wind. And then when that bubble bursts, a new one forms on the opposite side, and then it sort of pulls it back in the other direction. Very similar to the example of the swing. So you get this push and pull, it's actually a pull and pull, but from the opposite side of the building. And it's because of this that we tend to see the magnitude of these become bigger and bigger as the building becomes taller and taller. So the taller the building, and from our experience, if you are in Delhi, in the region, or Kolkata, where the winds are higher, then you can expect to start to see this crosswind effect become more dominant than the along wind for buildings higher than about 100 meters. In more benign climates such as Mumbai, perhaps closer to 150 meters, you could start to see this effect becoming more critical than the along wind. But just be careful that this is just a very, don't take this as hard and fast rule. I'm just giving you just a general expectation of what you would expect to see.
See, in general, a long wind response also has a static component, but a crosswind response doesn't have any static component. So, in case of small height buildings, certainly a long wind response is going to be larger than the crosswind part. This for sure. As the building height increases, there would be a competition between along and across, and beyond a certain height, at some particular critical wind speeds, the crosswind phenomena due to resonance is going to give a huge response. So there are three zones basically, and up to certain height, a crosswind response may be ignored even with the short height limits. That is there. There is nothing wrong. But Indian code is sure. There is nothing like not sure. Whatever the graphs have been given in the Indian code for a crosswind response estimation, they are from the researchers in Australia. I'm sure they are from the work of Professor Melbourne and Professor Saunders, and one from Professor Karim, USA. Is it, Tony?
Yes, correct. Yep. Now there's the new version of the crosswind force coefficients there's going to be an update in the next edition, which will hopefully come out before end of this year for the Australian, and this is based on the work of WindTech consultants. So we've looked at a lot of crosswind spectra from numerous past studies that we've done around the world, some in India, of course, and we've derived from these a revised set of curves. So the curves that you see now have been derived from the 1989 standard in the Australian standard, which are very similar to the one in the current one, the 2011. But in this new one, which I'm hoping will be the 2020, not 2021, you'll find there's some small changes to the curves where we found the very sharp peaks in some of the cases are not as sharp, and some of the low points need to be higher. So I'll if you like, I can see if I can share my screen.
Philosophically, a crosswind response, because there is no force, means no actual applied force in the crosswind direction. So force divided by stiffness and the response, that kind of formulation is not there. These are the actual measured forces in the crosswind direction, actual measured force spectra. And measured means they have been done on some specific buildings. So in some specific terrain categories. So whatever graphs have been given in the code for the force spectra value, they are specific to those buildings only, those orientations only, and those terrain categories only. Yes. We can use them as a guide for other matching or nearby ranges, but if something is deviating significantly, then they are not strictly applicable. You can refer to any
you can't get a 10 to 1 to 1 building, for example, and use the curves in there, because the numbers will be very different. So in fact, anything more than a 6 to 1 or 6 to 2 to 1, what you see in there is essentially the upper limit of what the code can cover. Okay, so anything more than that aspect ratio is generally not covered by wind codes.
Whatever here in the Indian code is reasonably okay. The only thing is the graphs which are there, probably again there was a point highlighted that while printing, that entire curve in the graph has been shifted a bit. So the value of the reduced frequency which is there for the corresponding is modified. Probably that is being discussed and being checked also. So maybe that will come as a correction soon. But otherwise, that is okay as a guideline to be used. and it is perfectly okay. We are not done. They are not the Indian wind tunnel test results. They are from international works only. And as Dr. Tony said, more additions would be there from Windtech work. So just wait for the things to improve. Yeah.
Yeah.
Yeah. And I think this is the last question from him about
Okay.
hourly mean speed and hourly mean wind speed factor. So, if possible, can you quickly specify what are the different factors used?
Factors are exactly same. They're all element. The K2 value is there. Earlier, there was a table in the code, table 33 in the earlier version, where the K2 values were defined. Those K2 values for hourly mean wind speed were different, and those for the 3-second gust were different. The ratio between the two was almost 1.5. Here, for K2 in the hourly mean wind speed, there is an expression added, which depends on the height at which the K2 is to be considered and the roughness height of that particular category. Only those two things are there. Z and Z0I. These two things are. This is the logarithmic profile which has been considered rather than the split power law. So the logarithmic profile has been used of the wind velocity and K2 has been defined. Otherwise, everything is same. Same K1, K2, K3 is there, K4 is there, and then K, KD, KC, and everything.
Right.
These values would be smaller than the 3-second gust.
Right.
In my last session, I explained also what is the effect of averaging time.
Right. Right.
Okay, we move on to the next.
Yeah.
Somebody
Sure.
else.
Sure. Yeah. So now there are few interesting comments which have come up. So which will be taking up from the line.
Hello.
Yeah, there is one question like, is there any device for wind isolation, like what we are using for a seismic isolation? Is there any
Oh,
device?
absolutely, yes. Windtech do design and can even provide a turnkey solution for such devices. Now, naturally, for wind, it's the best place to put it is as high up in the tower as possible. It is. We have done it sort of at, say, 3/4 height, but the amount of mass needed becomes a lot larger. So to get the most efficient size, it's best to have these devices near the top, and they can come in many forms. The cheapest form, which is similar to what we did for a building in Kolkata, was basically a sloshing tank. So we put a tank, its dimensions versus the length versus the water level needs to be tuned to the building's sway frequencies. And then we put devices along the way to absorb the energy from the motion of the water in the tank. So this is the most cost-effective method and very effective. In fact, in the recent cyclone Ampang that hit Kolkata, it basically the storm crossed Kolkata, right? Like the paths went across Kolkata, and the people in the building hardly noticed the movement from the damper that was installed in this building. So you can find more about this particular case from Windtech's website, which is windtechconsult.com.
Nice to see Govind Parchani on the session. Govind Parchani I know personally, and he is a knowledgeable person from Indore. He is currently, I'm sure, he's on a very senior technical position in CAT, Center for Advanced Technology, for Atomic Research. Is there? Govind, a very nice question, and as Tony explained, you need to have supplemental damping devices. There are many varieties available, and some very good examples are there worldwide. So more if you want on that, certainly if you write to Tony, they will give you more.
Yes.
Thank
So
you.
more than happy to assist if you have that requirement. And by the way, often the advantage with the liquid sloshing tanks is they are often needed anyway. So you're not adding to the cost at all for the building, because usually there's a need to have a water storage at the top of the building. for fire hydrants. So the chance of a fire breaking out at the same time as a strong wind is almost zero. So you can be confident that this is a very viable approach, very low cost when you think that you need to have a tank there anyway, but we just have to shape the tank in a particular way to work for you.
Right. Okay, one interesting question from Ankit. That maximum peak combined acceleration for residential building of more than 50 meter is 0.50 meter per second square, which is defined in the Indian code. So can you please throw some light on which condition it is needed to be checked?
It is given there. It is there written in the code also on the 10 years return period serviceability condition. You have to check this acceleration, and 0.15 meter per second square is not for residential.
I think it is for residential, but that's a 10-year return. That's the 10-year return, 1 in 10-year event. This is based on the work by done at the University of Western Ontario by Professor Izumov many years ago, about 30, 40 years ago. And then if it's a commercial building, then it's 0.25 square meters. If it's an office building. However, the ISO code has a more refined set of criteria. So I encourage you to look at these criteria with the Indian code criteria.
Because 0.25 mercantile and 0.15 residential.
Yeah, for the residential, 0.15, but it's a 10-year return, 1 in 10 year. In the ISO, you're probably thinking of the ISO, which is the 1 year, just 1 year return. It's a much lower number. In fact, it's for commercial, it's roughly 0.15. Residential, it's much less. So depending on the difference in the ISO, it's a function of the building's natural frequency. Okay, and that is being confirmed by numerous research done mainly in Hong Kong, and it's been shown that people's perception of motion becomes much more heightened where the building is stiffer. Okay, as the building becomes more stiff, people can feel the same acceleration in a more heightened way, and that's because our bodies naturally have a natural frequency, okay, and it's very close to 1 hertz, 1 to 2 hertz. So as the building moves, okay, the building sways at a higher frequency, as the frequency approaches 1 hertz, we feel, even subliminally, we tend to feel the effect of it in terms of feeling tired, sleepy, whatever. That feeling comes over a large percentage of a population. Obviously, every person is different, but these studies are based on many thousands of people, of subjects, and interviews with many people in Hong Kong, where there are many tall buildings, and so it's been established that there is a very clear relationship between perception of motion and the natural frequency. So I encourage you to, yes, use these guidelines in the Indian standard, but also use what's in the ISO standard. Okay.
I will have to leave the meeting at this point, and you may continue with the questions. Okay. It was nice. I have some work, so I have to quit.
Thanks.
Okay. All right. See you, Dr. Gupta. Thank you very much.
Thank you.
Okay.
So we will take up a few questions, right? So if possible, you can answer, or otherwise we may park it and then we may reply on the later. Maybe
Sure.
when video is getting published, right? Okay, see, one of the question, right? Yeah, it is related to IS 875, but I'm just reading out. If possible, we can answer. So, what is the question that in a basic wind speed map of IS 875 75 Part 3, adjacent places are defined with 50 meter per second and 39 meters per second. But there is
I, I find that strange myself, actually. Yeah, I find. Okay, so if you were to do a wind tunnel test, okay, we don't have to use the same wind speed map. Okay, we use our own analysis, and we know that it's not that dramatic, but it's maybe for sake of simplicity. But we know it doesn't happen like this. But in general, we tend to see slightly lower basic wind speeds anyway. For example, Mumbai, we find 40 meters per second is a closer number than 44. But that's another positive from wind tunnel testing. You already got a 20% advantage just before you even do any testing, just from the basic wind speed.
Okay, there is one more question. Like for seismic design, see what we are doing. That there is an accidental eccentricity. So whatever eccentricity is there, that we are amplifying. So is it also required to be done for the wind engineering also?
Okay, I think wind doesn't behave in the same way as seismic loads. So with wind, the response builds up gradually. With seismic, I think it's the opposite. You get a shock wave that comes suddenly, right? With wind, it's sort of the resonant part of the response starts to build up gradually over the duration of the storm. So it's a very different type of loading pattern to seismic.
Right. Okay, one question is that, like, for calculating the gust value, which method should be followed? Whether it should be graphical method or numerical method? Which is better one? I think that is the question.
For the gust value, the capital G. Well, it's really. I didn't know there was a graphical method. I thought it was always numerical.
Okay.
Yeah. What do maybe you can explain what's meant by the graphical method?
Exactly. He can put in the next chat, and then we may.
Sure.
Okay, this is a question from Ravi. Like in some foreign codes, a gust factor are also considering as a 0.85. So can you throw some light on this?
Oh no, that's not a gust factor. Okay. That the 0.85 is a effective direction multiplier. So what happens, for example, the ASCE has a 0.85 prefix. Okay, this, by the way, the coefficients are in the American, the ASCE, are combining the capital G, which is the gust factor, with the coefficient in one. Okay, but what they do, they don't account for directionality of the wind at each site, whereas we know that the wind is not the same intensity for each angle of attack. So to account for that in a probabilistic sense, okay, they apply a flat 0.85 factor. Okay, so this is what this is for, but that's not a gust factor.
Right, it's not a gust factor, right?
No, that's a more like a directionality factor.
Right. Okay, there is one more question. Like in the graph for crosswind frequency has a ratio of 6:1:1 and 6:3:1 and so on. So what if the building ratio is in between these figures?
Okay, there is a 6:1:2, and there is a 6:2:1, and there's a 6:1:1, and so on. Yep. So what happens? You can interpolate. You are permitted to interpret. For example, if you have a building that's, although I don't recommend the code be used beyond 6:1:1, I'm not sure. You'll find in the Australian code they removed the 9:1:1. because it should not be, for a building this slender, really shouldn't be in the scope of the codes. But if you're looking at a 4:1:1, then you can easily interpolate between a 3:1:1 and a 6:1:1 for the same turbulence. So if you're looking at, there are two levels of turbulence given. There's a 12% or a 0.12, and there's at 2/3 of the building height, and there's a 20% turbulence intensity. So you pick the appropriate level of turbulence intensity for your terrain and height, and then you look at whether it's the solid lines or the dashed lines, and you can interpolate. There's no problem with that.
Right.
And linear interpolation is fine.
Right. Now, this is an interesting question, I think, that how we can identify that the tunneling effect is there in the building or not. Any quick thumb rule or any special provision to identify?
Do you mean interference effects?
Yeah,
What?
I think it's talking about tunneling effects. So it's a kind of an interference effect. Yes.
Okay, I'll assume you mean interference.
Yeah.
Well, the good thing about the Indian code is probably the only code in the world, okay, where this issue has been raised, and it's a very important issue. There are some, reasonable attempts in the Indian code to present this, and you'll find that in section 9.1, okay, in figure 8 of the IS 875, the general rule is sound, although, as I mentioned before, be careful if you are finding that the crosswind is governing. This 1.35 factor should increase to 1.5 at least. And in any case, you should consult a wind tunnel laboratory such as WindTech Consultants. If you're finding that the crosswind is governing, that's an indication for you that this building is dynamically enough, sufficiently dynamic to warrant a more detailed study. Any other questions? I think you're muted.
Yeah. Okay, so I think still questions are coming up. So maybe this is the last question, we can take it up. And then after, if the more questions are there, we'll compile, and then we may have a separate session, maybe probably in the future, right? Yeah. So
Sorry.
this is a,
You're going to need to explain PBD. What's
PBD is a performance-based design.
Oh, okay.
So in a seismic design, see, there is a performance what we identify, let's say in terms of a deflection or in terms of, let's say, the strength of the building. We have certain performance criteria.
It's very difficult to codify performance-based design.
Yeah.
But at WindTech, we have developed a performance-based technique for analysis of wind tunnel results as a standard scope. So all projects we do anywhere in the world are subject to the more rigorous performance-based analysis. We don't just look at each wind direction independently and pick the largest directional response. That is not performance-based design. Okay, so we look at a more holistic experience of the building over its life as part of our wind tunnel analysis, looking at effects of all 36 different angles of attack of wind, and we integrate the contribution of these. The effect of our performance-based approach is that we tend to come up with, on average, about 12% lower loads than the standard wind tunnel methods that are done by other consultants.
Right. So still there are a couple of questions. Can we take it up? Yeah. Hello, Tony?
Yes.
Yes.
It's up to, maybe I could do another one, just one last question then.
Yeah, last question. So this is the last question. Then we will close.
One last.
Yeah. So the question is, let's say between CFD and wind tunnel comparison, what may be kind of a pros and cons? Which will be better?
Sure. Okay. All right. So CFD we use CFD a lot, but mostly for environmental modeling, thermal comfort. Sometimes for fairly unusual situations, we need to use a hybrid of, like for wind loading, we very rarely, but where wind tunnel testing has limitations in terms of the need to look at macro scale and micro scale at the same time, sometimes we have a combination of CFD and wind tunnel, but that's extremely rare. But I would not use CFD alone for determining response of a tall building. Why? For a number of reasons. Computational fluid dynamics models, all different turbulence models, generally assume an isotropic environment, meaning the turbulence is the same in the horizontal, the crosswind, and in the vertical is uniform, which we know is completely not the case. Results from CFD are still in development phase. The CFD environment has not yet developed sufficiently to give us the level of confidence that we can get from wind tunnel test. Okay, we have done comparison between wind tunnel testing and full-scale testing, and we're generally within a few percent. Okay, you would be lucky to be within 40-50% from a CFD, unless you know what the answer is. If you know what the answer is before you do the CFD, it's very easy to manipulate the turbulence factors to get something within a close range. But that doesn't, it defeats the purpose. Okay, you wouldn't go alone on CFD. But there are applications for CFD in tall buildings where obviously wind tunnel can't go, and such as looking at stack effects, environmental, like thermal comfort in semi-open spaces, in a open area, a common area in a podium of a tall building, for example. These are things that CFD can be used as a very useful tool. And often at WindTech, even in those situations, we calibrate the CFD model against measured boundary conditions that we have obtained from the wind tunnel test to improve the accuracy. I guess that would be the last question.
Yes.
Okay.
Questions are coming up, so I will do what I will do. I will summarize those questions, and then I will then we may talk it offline. And maybe if possible, you can also participate in the wind tunnel testing session. I think that will be very much interesting for all the.
Sure.
Yeah.
Okay.
So
we'll hope to see you next time.
Yeah, definitely. So we'll meet again. So thank you, Tony. Thanks a lot for giving very detailed and very interesting answers to the audience, and I'm sure that a lot of knowledge is exchanged in say last 1.5 hours. Okay, so
Okay.
now,
thank you very much for your attendance.
Yeah,
Okay.
yeah.
Bye.
So we are signing off. Bye.
See you.
Bye.
Bye.
Yeah. Bye.